In this lesson, we are going to look at simplifying radicals. Now remember, a radical is a root. A root is an operation that either, if the index is 2, finds 2 equal factors and takes one of them. If the index is 3, finds 3 equal factors and takes one of them, etc. We're going to focus today on roots, or the square roots and cube roots, 2 and 3 index. Okay? But you can go up as far as you like, right? You can have a 5th root and 8th root. That whole thing is called a radical. The index tells you what root it is. The inside number is the radicand, okay? The number you are rooting, okay? So, if you have a root like 45, which is not a perfect square, you can simplify it. Because you can't actually take the square root of it and write the exact number since it's irrational, the best we can do is simplify. And simplifying means find a perfect square that divides evenly into 45 so that we can reduce. So I can see that 9 goes evenly into 45 because 9 is a perfect square. So I can break 45 into 9 multiplied by 5. And I can take the square root of 9, right? I can even break it up further, multiply. So when you're multiplying, you're allowed to break it up like that, right? If you were adding, you would not be, but multiplying you can. And so the square root of 9 is 3, and the square root of 5 I can't do, so I write the square root of 5, which we can squish back together, meaning 3 times root 5, right? So to simplify a radical, this is called an entire radical when everything is underneath the root sign. We can simplify an entire radical into a mixed radical by looking for a perfect square that divides into it, that is a factor of it, and breaking it down and taking the square root of the perfect square. 5, we cannot take the square root, so it stays underneath the root sign. All right? So root 45 is equivalent to 3 times the square root of 5. They are the same. 3 root 5 is the simplified mixed radical. It's pretty important in this unit to really have in your memory bank your perfect squares and some of your perfect cubes. You should recognize 4, 9, 16, 25, all the way up to probably 144, 169 as your perfect squares. Those are common ones you'll need to look for as factors, right? They're the ones you care about. You don't care that 15 goes into 45 because you can't take the square root of 15. It's not a perfect square. Same thing with perfect cubes. There's not as many because they grow so fast, right? It's easy to generate. 2 cubed, 3 cubed, 4 cubed, 5 cubed, 6 cubed. So if you have difficulties with memory, you can always just generate these yourself anytime you need them and write them down and have a list for you. So today let's practice simplifying our squares. Okay, so this radical is a square root of 20 and I want to simplify it. So using my perfect square list, since it's square root, I look at perfect squares. If this was a cubed root, I'd look for perfect cubes. So I look for the largest perfect square, which is 4, that goes into 20. So it becomes root 4 times 5. I always write the perfect square first because I'm going to take the square root of that. The square root of 4 is 2. I don't write the square root of 2 because I took the square root of 4. That operation's gone. I cannot take the square root of 5, so the operation is still there. I have to write it. So this is square root of 20 is the same as 2 root 5, or 2 multiplied by the square root of 5. Let's try root 72. If you're watching this video, it's a good idea to pause it, try the question, and then come back and unpause it and see if you got it correct. Now, most people do this. You're not wrong, but if I do it this way, whoops, I make a mistake. If I do it this way, I'm not wrong, I'm just not done. Because if you look at 8 inside, there's still a perfect square that divides into 8, right? 9 is a perfect square that goes into 72. It's just not the largest one. So if you did this and realized, whoops, I must not have picked the largest perfect square, that's okay. You always have to check your radicand and go, do any of these numbers go into it? Oh, yes, 4. That's okay, just keep going. Just keep going. Break down 8 into 4 times 2, right? The 3 just tags along. So I get 3 times, and the square root of 4 is 2. I can't take the square root of 2, so it stays underneath. And now I can multiply 3 by 2. Right? So it was more work, but it was possible. So the key is, can you always find the largest perfect square that goes into this number? If you had noticed right off the bat that 36 times 2, you would have saved yourself a lot of work, because the square root of 36 is 6. And there you go. You get the same answer with a lot less work. All right, so let's try 3 root 56. What is the biggest perfect square that goes into 56? A lot of people are like, well, 8 times 7. But 8's not a perfect square, and 7's not, so that doesn't help me at all. So I have to take 56 and go, all right, well, let's go back to my list and let's think. What are some numbers that go into it? Obviously, it has to be less than half of it, right? 25 times 2 is 50, so it's not 25. What about 16? 56 divided by 16 is 3.5. Ah, that didn't go evenly. What about 56 divided by 9? Ah, that doesn't go evenly. What about 56 divided by 4? It's my last chance. Oh, finally, 4. 4 goes into 56. If nothing went in, then I couldn't simplify it, but 4 does go in. So the 3 outside is still there. It's 3 times the square root of 56. So I just use brackets to remind myself it's multiplication. And so I'm going to get the square root of, what did I say, 4 times 14, right? And the square root of 4 is 2. I can't take the square root of 14, right? And I don't see a perfect square that goes into it, right? 4, 9, 16, right? I don't care that 2 and 7 multiply to give 14. That doesn't matter because they're not perfect squares. Now I can multiply the 3 and 2 since they are both outside of the radical. Then we can multiply it, and the root 14 stays. All right, so this is simplifying radicals. I can even put a fraction out front. That's okay, right? You'd still do the same thing. The fraction would come along, and you just worry about the inside right now. What number goes into 270? I see 9. And again, you just go down the list and try. Here's a tip. 9 times 30. I look at 30 before I go on. Does a perfect square go into 30? 4, 9, 16. Nope. So that confirms that I found the biggest perfect square, right? So you just double check before you move on. That's helpful. If not, then you can erase and keep going. So now I write the 2/3. The square root of 9 is 3. The square root of 30 stays square root of 30 because there's no perfect square in it. And now I can multiply 2/3 times 3, which is 6 over 3, which is 2, or you could cancel however you want to do it, and you would get 2 root 30. All right, so even if there's a fraction in front, it just tags along, and then you multiply the numbers outside of the root sign. I can do it with variables. Okay, what is the biggest perfect square that divides into x to the 7th? Well, remember last day we learned that even powers are perfect squares. So even powers are perfect, or even exponents, I should say. Even exponents are perfect squares, because if it's even, I can break it into 2 equal groups. So I need to take this and multiply it by the largest even exponent. And then what's next, right? X to the 6th times x to the 1 is x to the 7th, and x to the 6th is my perfect square, right? Because it has an even exponent. So since it has an even exponent, I take the square root of x to the 6th, right? X to the 6th is x to the 3 times x to the 3. That makes it a perfect square. The square root of it is just one of those 2 equal factors. So the square root of x to the 6th is x to the 3. I can't take the square root of x, so it stays underneath. It stays underneath. That's a trickier one. I could mix numbers with variables, right? So you just do them separately. You do the 8, then you do the x to the 6th, then you do y to the 3. 8, which is 4 times 2, right? X to the 6th is a perfect square, so I just leave it. Y cubed is not, so I have to break it down into y squared times y. Right, that's y to the power of 3. Then let's highlight all my perfect squares. Those are my perfect squares. Those are the ones I'm going to take the square root of and put on the outside of the root. So the square root of 4 is 2, no longer needs a root sign. The square root of x to the 6th is x cubed. And the square root of y squared is y. All of that has now been calculated. So now I write my square root sign and whatever's left. I still have my 2 and I still have my y. And that's your final answer. So that I would consider, those two I consider pretty tough questions. You'll do a lot more of that in grade 11. Okay, in grade 10 we should focus on the ones with numbers, but that just takes you to the next level. We could do the same with cubed roots. So remember, what are our perfect cubes? 2 times 2 times 2 is 8. 3 cubed. 4 cubed, see how fast it grows? There's actually, I find cubed roots easier because there's less numbers to check, right? 6 cubed is 216. I could keep going, 343. Like, they get fast really, really fast, big really, really fast. So 250, I look for the largest number that goes into 250. This time it has to be a perfect cube since it's a cubed root. And 125 goes in twice. So this time, because it's a cubed root, I have to write that index. Otherwise, it looks like a square root. 125 multiplied by 2. The cubed root of 125 is 5. 1 of 3 equal, right? And then I have to write cubed root 2. Make sure you always write that index. So important with cubed roots. Every time, you can't leave it out, okay? So 24, the largest number, well, there's only one to check. It's 8, right? Well, 8 goes into it. So it becomes 3, and I'm going to use my brackets just to remember that the 3's out front. Becomes 8 times 3 inside. The 3 just tags along till the end. The cubed root of 8 is 2. I cannot take the cubed root of 3, so that stays inside. Now that I have simplified the root part, I can now multiply the two numbers outside, and it's multiplication, not addition, right? Because they're squished together for multiplying. You'll only add them if you're like collecting like terms and combining how many of them you have. And there you go. We could do it with variables. Do you remember what kind of power, what kind of exponent creates a perfect cube exponent? Right? It has to be a multiple of 3. If it's a multiple of 3, it's a perfect cube because I can split it into 3 equal groups. And it has to be the exponent. So the largest perfect cube that goes into x to the 10 is 9. So I can break it into x to the 9 multiplied by x to the power of 1. The cubed root of x to the 9, if I break x to the 9 into 3 equal groups, it would be x cubed times x cubed times x cubed. So the cubed root of that is one of those 3 equal factors. So the cubed root of x to the 9 is x cubed. And I cannot take the cubed root of x, so I have to write the cubed root of x. Right? You can see how exponents and indexes, you got to be neat and tidy. They can get messy. Again, that would be like a grade 11 more difficult problem. We'll focus on the numbers, but we get the idea. We could also take a mixed radical and write it as an entire radical. So instead of simplifying and getting perfect squares and square rooting them, we can put this back inside. So how can we put this back inside? Well, the square root of what is 2? The square root of 2 squared, or the square root of 4, right? So you're kind of undoing the operation. When you take it out, you're square rooting. So when you put it back in, you want to square it, right? So if I have 2 root 18, when I put the 2 inside, I have to square it, right? You have to square it back inside because you square rooted the 4 to get the 2, so you have to undo the square rooting. So I get 4 times 18, which is 72, right? So here I would have, putting the 4 back in, I would get 4 squared times 8, which becomes 16 times 8, which is the square root of 128. So if you have a square root, you want to go back to an entire, you have to square it when you put it back in. If it's a cubed root, Well, when you put the 5 back in, the cubed root of 125 is 5, so the 5 has to be cubed when you put it back inside. So I would cube the 5, and the 9 is, there's only one 9 in there, right? So, 'cause it wasn't a perfect cube, so it stayed there, so it's still there. So I go 125 times 9, and that becomes the cubed root of 1125, right? If I was to simplify that, I get that. If I want to go back to an entire radical, I would go in that direction. Last question. How can I use radicals with my Pythagorean theorem? Well, we know that a squared plus b squared equals c squared. Or, since I know c and I don't know a or b, we can rearrange this. A squared equals c squared minus b squared, right? Or b squared equals c squared minus a squared. A and b are interchangeable. They are the legs. This is c, the hypotenuse. So, let's make the one by itself x. X squared equals c, the hypotenuse, root 123 squared minus b squared. Right? If you're square rooting and squaring, they cancel each other out. They're opposite operations. Same thing here. They're opposite operations, right? You could take on your calculator and go 123 squared and then square root it, but you'd be right back at 123, right? Because they're inverse operations. They take you back to where you were. So you get x squared equals 123 minus 51. And so 123 minus 51 is 72. And now that's what x squared equals, so now you have to square root it. And I want you to leave your answer in the simplest mixed radical, because that's not a perfect square, right? So it would give me an irrational number. It's an irrational number, give me a decimal. So if I want the exact answer, I have to leave it as a radical or a simplified radical. And like we showed earlier, this is 36 times 2, which becomes 6 root 2. X is 6 root 2 in exact form.